Okay, everyone. We've been talking about exponential growth up until this point. Exponential growth modeled the temperature of an object that you take out of the oven. It modeled population growth. It modeled growth of or the decline of contagious people from a disease. And the last thing we looked at was radioactive decay. Right? It modeled the decay of radioactive substance. So it's very important in describing all of those things. And now we're going to go on to other kinds of separable differential equations, which are related to exponential growth, but a little bit different. So before we jump off of this one entirely, I want to just one more time explain the significance of exponential growth, because you hear people use the term "this thing grew exponentially." You hear that a lot, and you should know exactly when something is exponential growth and when it isn't. Lots of things grow fast, but they don't grow exponentially fast. Okay, so anyway, exponential growth basically means it's an equation that looks like this. It's constant times e to the kt, where k is if it's going to be growth, where k is something greater than 0, and so you get this exponential growth. And the two things you should realize about exponential growth, one we've talked about already, but I'll mention it again, and that is that with exponential growth, the rate of increase, which is the slope of the function, is proportional to the height of the function, right? If you take the derivative of this thing, dy dt, what are you going to get? You're going to get k a e to the kt. Agreed? And this is just the function right there, which is k times y. So when you have an exponential function like that, the rate of growth is proportional to the height of the function. The higher the function goes, the steeper it is, okay? Which means it's just building. It's just building the momentum, building whatever it is it's doing. It just goes more and more and more. It goes wild. It grows exponentially, okay? So that's one thing that's true of exponential growth. The other thing true of exponential growth is that if you take any 2 points on this axis, which are just 1 unit apart, I don't care, let's just call them 5 and 6, just to be specific, 5 and 6. Notice that what do you have? You have y of 5 is equal to a times e to the 5k, and y of 6 is a times e to the 6k. And so notice that in order to get from here to here, y to the 6th is just what? It's a e to the 5k times e to the k, right? Because if you add those exponents, you're going to get a e to the 6k, which is your y of 6. Okay? So in other words, when you go from one point to another here, what do you do to the function? You multiply whatever this value is, you multiply it by the same value over and over and over again. You multiply it by the same value over and over and over when you go from here to here. If I go from y of 7, it's going to be a e to the 7k. Y of 8 is going to be a e to the 8k. Notice that that's just a e to the 7k times e to the k again, because this plus this is e to the 8k. So you always multiply this value by the same value in order to get this. So as you go from here to here, you just keep multiplying. You keep multiplying. This is all the more obvious if instead of using e, if you use 2. 2 to the x. If this were the function 2 to the x, then this would be 0, this is 1, this is 2, this is 3, 4. So here you are, 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, and again, I don't have the graph right. 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32nd, 2 to the sixth is 64. and so on. Notice that as we go from one point to another, you just keep multiplying. In this case, instead of multiplying by e, we're multiplying by 2. So you just multiply by 2 over and over and over and over again. Okay? So that, again, that's exponential growth as well, or geometric growth. Both of those terms are used. This is in stark contrast to linear growth. Linear growth, let's just take the easiest case here. Y is equal to 2x. Okay? To 2x. Now, what do the values look like? Here you are at 1, 2, 3, 4, 5, 6, and so on. What are the values of the function? Here it's 2, here it's 4, here it's 6, here it's 8, here it's 10, here it's 12. Notice, what did you do here? You multiplied by 2. The value of the function you multiplied by 2 every time you went. Here, what do? In order to go from 4 to 6 to 8 to 10 to 12, what are you doing? You're not multiplying by 2. You're obviously adding 2 each time. So when you have linear growth, you're adding as you go from here to here. When you have exponential or geometric growth, then you're multiplying. So, of course, you know when you multiply by numbers, things grow much, much faster than when you just add numbers. Okay, so that's why geometric or exponential growth grows so much faster than linear growth. Okay, so that's an example. So, so anyway, let's do one example. This is one of my favorites, which just gets this point across. I call it the grandpa problem. And again, this is in the textbook, so I won't do all the work here. But read about it, and here's kind of it is filled in. So you have two grandpas who 200 years ago, we'll call them Abe and Bob for A and B. And 200 years ago, they each put $10 in the bank at 6% interest, annual interest. Okay, compounded annually. Okay, so 200 years ago, you have these two great-great-great-great-grandfathers, and they put $10 in the bank for you, and every year you get 6% interest. But they give different directions. Here's the directions that Abe has. His directions are this. Every year, the bank is to take that interest and to pull it out of the bank and to give it to you or give it to your ancestor so that they can just keep it in a piggy bank. Okay, so the interest, the $10 stays in the bank, but the interest keeps coming out and gets just put in a piggy bank. Okay, so let's think about what's going to happen. Okay, at year 0, when they put it in, there's going to be $10 in the bank. Agreed? At the end of the first year, you've got $10 plus 6% of 10 is 60 cents. So plus 60 cents. So you've got $10.60. Okay, the $10 stays in the bank, and the 60 cents you pull out and you put that in a piggy bank someplace. At the end of the second year, you've had this $10 in the bank. That earns another 60 cents. And so you take that 60 cents and you throw it in with the original 60 cents, and now you have 60 plus 60, which is going to be $1.20. So you're going to get $11.20 total, because each of those 2 years you made 60 cents and you got the original 10. At the end of 3 years, you're going to get $11.80 because you earn another 60 cents. At the end of 4 years, you get another 60 cents, so it's going to be what, $12.40, I believe. At the end of 5 years, you get another 60 cents. You're going to be at $13. And of course, it keeps on going. At the end of 200 years, you've got what total? You have 60 cents times 200 years, and that's going to be $120. Plus, you have the original $10, so that's going to be $130 total. Okay, there's your total amount of money after 200 years. Okay, so notice that's linear growth, because you start off with 10, and every year you add 60 cents. So every year you're adding the same amount each time. See that? So it's a slope of 0.6, and so that's your linear growth right there. And so at the end of 200 years, it's going to be up to $130. So let's say linear growth. Okay? Bob, on the other hand, is lazier, okay? Or his descendants are lazier. He just says, heck, just keep the money in the bank. Don't bother taking it out each time. We'll just take our chances and we'll just let it all accumulate in the bank. Okay, so let's see what happens with Bob. Every year, the interest gets added to it. So beginning year, of course, $10 again. At the end of the first year, the easiest way to do it is to do it like this, is to think of it like this. You take 1.06 times the 10. Why do you do that? Because when you take 10 times 1, that gives you your principal back. There's your $10 back again. But you also take the 10 times the 0.06 to get the interest. And so that's going to be $10.60. Same as this person. At the end of the first year, you've got $10.60. Okay? At the end of the second year, you take this amount of money, $10.60, that's how much is in the bank, and again, you multiply that by 1.06. Again, why do you do that? Because when you multiply it by 1, you get the principal back, which in this case, it's $10.60. That's how much you had at the beginning of that year. Plus, you take the 0.06 times that, and that's your interest. So notice when you do that, what you're really doing is you're taking 10 times 1.06 squared, because you multiplied it here and you also multiplied it there. Okay? And I'm going to let you get these numbers. Well, heck, I will do them as long as we've got a little bit of time here. So it's going to be 1.06, enter, 2, there. Whoops. This is, do it again. 1.06, enter, 2. Okay, there it is. And now multiplied by 10. And I get $11.236, so it rounds to $11.24. So notice that by keeping it in the bank, we've got an extra 4 cents from what you have there. At the end of the third year, notice we're going to get 10 times 1.06, and we're going to multiply it by a third time. And we're going to get $11.91. So now we've got 11 cents more. Okay? Notice the amount is increasing. At the end of the fourth year, $12.62. And at the end of the fifth year, $13.38. Okay, so at the end of the fifth year, you got an extra 38 cents just from leaving it in the bank. Okay, so notice that this growth here is exponential growth, because every year you are taking what's there previously and you're multiplying it by something, right? You're taking the previous amount and you're multiplying it by 1.06 rather than adding 60 cents to it. So that's the definition of exponential growth. To go from here to here, you multiplied it by that. And since that's a number bigger than 1, it's going to be an increase. So it's going to increase. So it's an exponential increase. Notice that it's exponential because you're multiplying, okay? And the question is, how much will that end up being by the end of 200 years? And heck, I'm not going to give it to you. I'm going to let you figure it out for yourself. You can see how to do it. So it's going to be $10 times what? 1.06, how many years? After 200 years, Don't do it until you've guessed at it. Go ahead and guess at it. How much it's going to be bigger than 130? How much bigger? By the time you were here, you were 38 cents bigger. By the time you're here, how much are you going to be bigger? Are you going to be double? Are you going to be 10 times that? Holy smokes! What are you going to be? So you figure it out, and you'll see the difference between exponential growth and linear growth. And once you understand exponential growth, it can change your life. Because then you start thinking, aha, hey, I'm maybe, if you're at a typical college student, maybe in your 20s or something like that, and you think, wow, I've got most of my life ahead of me, then given the fact that money grows exponentially and the stock market grows exponentially, if you can live a lifestyle that allows you to squirrel as much money away, and obviously to keep from borrowing too much money, because then all this works against you, but to keep from borrowing too much and to squirrel as much of it away as you can, and whatever you have borrowed to pay back as much as you can, so that you can start getting this exponential growth, it makes a huge difference. And this is over 200 years, obviously, but even over the span of a lifetime makes a big difference. So that's why a college education and liberal education can really liberate you, because it gives you, if you understand those things, it can lead to a better life, just as you understand, in this case, just how numbers work and the difference between exponential and linear growth. So very good.